Hello, my name is Gabriela Bobadilla Barron from Simvestab, and today I would like to present our work CNOF thin films deposited by ultrasonic spray pyrolysis for gas sensor application. Gas sensors are very important for applications such as environmental monitoring, industrial safety, and the detection of gases. Among different metal oxide semiconductors, zinc oxide or CNOV is particularly interesting because of its low cost, chemical stability, and sensitivity to changes occurring at its surface. In our work, we use fluorine-doped CNOF can modify the electrical and surface properties of CNOF, making these materials attractive for gas sensing application. The basic sensing mechanism is shown here. When CNOF is exposed to air, oxygen molecules are absorbed on the surface and capture electrons from the materials. When a reducing gas, such as carbon monoxide, interacts with these absorbed oxygen species, electrons are released back into the material. As a consequence, the electrical resistance of these changes, resistance is what they use to detect the presence of the gas. For the experimental part, CNOFs thin films were deposited on glass substrates using ultrasonic spray pyrolysis or USP. We use zinc acetate dihydrate and the zinc precursors and ammonium fluoride as the fluorine source. The films were deposited at 75 degrees Celsius using deposition times of 8 and 40 minutes. Now, looking at the structural and morphological characterization, the X-ray diffraction results confirm the formation of polycrystalline CNOF with a hexagonal Goursat structure, with preferential retention along the 002 plane. Importantly, no detectable secondary phases were observed. The same images show relatively homogeneous and compact surface formed by interconnection grains. This morphology is particularly relevant for sensing application because the grain surface and grain boundaries provide sites where gas molecules can interact with the sensing materials. Regarding the optical properties of the film, show high transparency in the visible region and clear absorption edge in the near ultraviolet region, which is characteristic for CNOF. Differences between the examples are mainly associated with changes in film thickness and surface morphology. Finally, this is probably the most important result of our work. Here we evaluate the electrical resistance of the CNOF films as a function of carbon monoxide concentration at different operating temperatures. As you can see, the electrical resistance progressively decreases as the CO concentration increases. This behavior confirms that the CNOF films have a clear electrical response to the presence of the carbon monoxide. The response also changes with operating temperatures, indicating that temperature plays an important role in the interaction between the gas molecules, absorbed oxygen species, and CNOF surface. In conclusion, we successfully deposited fluorine-doped thin films by ultrasonic spray pyrolysis. The films exhibit a polycrystalline Goursat structure, relatively homogeneous morphology, and high optical transparency. Most importantly, the films show a clear decrease in electrical resistance with increased CO concentrations, demonstrating their sensitivity to the target path. Therefore, this result suggests that CNOF thin films deposited by USP are promising materials for the development of resistive carbon monoxide gas sensors. And that's all, and thank you very much for your attention.